So here's our first sample problem for this topic. It says here, determine the phase of the water for the following condition: 120 degrees C temperature and the pressure of 500 kilopascals. And also draw the TV diagram, or plot it in the TV diagram. And then also find the properties such as the specific volume, internal energy, enthalpy, and the entropy. Okay, so we don't know yet. I mean, at this point, we don't know if it is in the compressed liquid region, is it in the saturated mixture region, or is it in the superheated vapor region. So we are going to check first the table 1. I think the table, since we have here the temperature or pressure, so we can use actually either which. So we'll use the table 1 b.1.1 to check. Okay, so let's write here. So for the solution, so first one is to check the condition, check the phase of the condition using, of course, the given condition using table B. So table B.1.1. So here's the table B.1.1. So table B.1.1. So our given temperature is 120 degrees C. This is 120 degrees C. So here's our data. So at 120 degrees C, the pressure is 198.5. So let's write it here. At temperature, okay, so at T is equal to 120 degrees C, the pressure is P is equal to 198.5. P is equal to 198.5 kilopascals. So this is the saturation pressure, and the given pressure is 500 kPa. So compare this. So if you see, you need to compare this pressure to this given pressure, and we see that the P given, so P given is, so 500, that's right, 500 kPa is greater than the P. Let's write the subscript here, P sat. Okay, P sat of 198. So if the pressure is greater than the saturation pressure, so that means, if here's our line here, so supposedly the pressure here is 198. It says 198.5 kPa. So if this is 198.5 and the given pressure in the problem is 500, that means there's too much pressure. So pressing the substance, that means that the condition would be in the compressed liquid region. So that means we are in compressed liquid region. So 500 kPa is greater than Psat, therefore we are in or the condition, therefore the condition is at compressed liquid region, compressed liquid region. Okay, so if we check B.1.2 when using 500 kPa, so let's do that. So 500 kPa, so here we are. So 500 kPa, and the temperature is, T saturation is 151.86. So the temperature that's given is um, 120. So if we use this data, it's actually the same thing. So that means the temperature here, if we use the temperature volume diagram, so the temperature here for Tsat must be 151.86. So 151.86. However, our our given value is 120, so that means it's somewhere lower. So it should be on this region, compressed liquid region. So therefore, that's in compressed liquid region. So now let's draw the phase. So now draw the phase. So using temperature and volume, and here's our saturation curve, and here's our pressure line. So our state is here. So that is in compressed liquid region or subcooled region. So it's not just enough to just draw this, but you also have to put the data. So Tsat is, let's say, this is 151.86. Then the pressure here is 500 kPa. So our given condition is just 120 degrees C. Okay, so next one is, now that we know that we are in the compressed liquid region, then that means we can now go to the table B.1.4. So for the compressed liquid, since this is available already, let's write here compressed liquid. So using table number 3, using table B.1.4 at T is equal to 120 degrees C and 500, and P is equal to 500 kPa. Then what's going to be the value for V, U, H, and S? Okay, so here's our condition again: 120 degrees C and 500 kPa. So 120. So first check this 500 kPa. Right, so 500 kPa and 120. So here it is. So our value is, let's copy this. So V, U, and H. So we can copy. So V is equal to 0.00106 T cubic meter per kilogram, and U is equal to 503.37. This is kilojoules per kilogram. H is 503.90 kilojoules per kilogram, and then for the S, 1.5273 kilojoules per kilogram Kelvin. So that's the value for this condition. So now let's try the approximation. Using approximation method. So recall that it's just simply the V value is just simply the V F of the temperature condition. So at what temperature? At 120 degrees C. So 120 degrees C, and then U, U, H, and S. So U is UF at 120 degrees C, and H is HF at 120 degrees C, and S is SF at 120 degrees C. Okay, so let's go back to our table. I think we'll use table. So using table B.1.1. So at 120, what's this value? It's the value of VF. So here it is. Okay, so VF is 0 point, here's the VF, 0.001060. So VF, VFG, VG, so this will be U, 503.48. And then in the next page, we have 120 again. And what we need is 503. So HF and SF. So HF is 503.69. Or I think it's better if we use this. So 120 and here. So go here. So 503.69. So 503.69, and the SF is, what's the SF? 1.5275. So 1.5275, and the unit is in kilojoules per kilogram K, kilojoules per kilogram, kilojoules per kilogram. Okay, and since we must not go beyond this borderline, so we have to change this. Okay, so I think that's all for this problem. So if we have a recap on what we did, so first is we are asked to find the phase of the water for this condition, 120 degrees C and 500 kPa, and also to find the other properties. So first step that we did was to check the phase of the given condition, and we use this table B.1.1 or 0.1.2, the pressure table, and then just check whether it's greater or below the saturation properties. So if the pressure, let's say the 500 kPa, is greater than the saturation pressure, that means it is a compressed liquid. But if we take, or if we look at it in terms of the temperature, if the temperature here, the T saturation is, let's say, 151, and we are lower than 151, that means that we are in this compressed liquid region. So now that we are in this compressed liquid region, we can use the table B.1.4 to determine the properties, or we can use an approximation. Okay, so that's all for this sample problem number 1. So next problem that we have, it says here, determine the phase of the water for the following condition, 120 degrees C and 0.5 cubic meter per kilogram, and also draw the TV diagram, or plot the conditions in this TV diagram, and also find the properties V, U, H, and S. So I think we don't need to find this because this is already given. So we are just asked to find the internal energy, the enthalpy, and the entropy. Okay, so first step, as always, is, so for the solution, So for the solution, first step is to find the find the phase of the given condition. So we'll use let's say using table B.1.1. So the temperature is 120 degrees C. That means we'll use B.1.1 120. So here's our values. So the V value is 0.0 so 0.001060. So I think it's just the same. So 0. So this is okay. So at T is equal to 120 degrees C, the VF value is 0.00160 kilogram, cubic meter per kilogram. Okay, so we are going to check first. So check first if, so what I'm going to do is to check this point. So what is the value of VF, what is the value of VG, and compare if the 0.5 cubic meter is greater than VF or greater than VG. So VF is 0.00160 and then VG is, so VG is equal to 0.89186. 0.89186 cubic meter per kilogram. So therefore our given V is 0.5. So therefore since the given is V is equal to 0.5 cubic meter per kilogram, therefore it is in the saturated mixture region, because 0 point, so 0 point, or let's just write VF is VG. So that's our condition. So now let's plotting now in the TV diagram. So plotting now in the TV diagram, we have TV, and here's our line, and our condition is right here. So temperature is still the same. That means this is T is equal to 120 degrees C, and the pressure here is we can just check it later. Okay, next one is, okay, so since we are in mixture, then we know this value VF, we also know the V here, and we also know the VG. So since we are in the saturated mixture region, therefore solve for quality X. So we will need this X value so that we can solve or we can find the other properties. Okay, so recall that V is just simply equal to Vf plus x Vfg. So since we have this value, this Vf and Vfg, therefore we can solve for x. Therefore x is equal to V minus Vf all over Vfg. So if we substitute the values, what we get here is, I think, 0. Alright, so let's solve this. 0.5 minus the 0.006, 00106, and here the Vg is 0.8908. So 0.8908. So 0.5 minus 0.00106 divided by 0.8908, and we have 0.56 and 0.56. So 8908. So 0.56. Okay, so next is to solve for other properties. So u will be simply uf plus x ufg, and then whatever the values here, and then for h, that is equal to hf plus x hfg, and here for the s is equal to sf plus x sfg. So what is uf? Then we go back to our here. So uf is 503.48 plus 0.56, and then times the ufg. This is 2025. So here's the ufg. So 2025.76. So 20.25, sorry, 2025.76 ufg. This is 503.48 plus 0.56 times 2025.76. This is equal to 1,637. It's 1,637.9. The unit is kilojoules per kilogram. And for HF, we still do the same thing. We just have to find here the value of HF 120. That means here is our here. So for HF, we have 503.69. So times the X and HFG of 2202.61, and for S is 1.5275 plus X times 5.6020. Okay, so next is to solve this. We have 503.69. It should be plus, right? So this should be plus. So plus X. What is X? It's 0.56 times 2202.61 is equal to 1737. So 1737. 1737.15. So 0.15 kilojoules per kilogram. Then for S, we have 1.5275 plus the X 0.56 times 5.6020. And what we have is 4.66 for kilojoules per kilogram Kelvin. Okay, so let's check if it makes sense. I mean, if the value makes sense. Our SF is 1. SF is 1.5275, and this one is the SG is 7.1. So we should be in between the range. So in between of 1.5 to 7.1. So 1.5 to 7.1, we are somewhere in between. So this is correct. And then the H value is so the H value is 500 to 2700. So we must be somewhere in between. Right, so 1737. So I think we are still in between, and therefore that's the we can also check the specific volume. So anyway, it's a lengthy computation, but actually the process is repetitive. You just have to check, make sure which region does the condition falls into. Okay, so just to do a recap again, first what we did was to check the phase. We used the table 1.1, and then check the ranges of the saturated liquid and the vapor regions for the specific volume. Then compare, and we have found out that our phase is somewhere in inside this saturated mixture. And then since for the specific volume everything is given, then therefore we can find for the quality X, and this quality we use that in solving the other properties. So we use these relationships for the U, H, and also the S. Okay, so I think that's all for this sample problem.